Hi, this is David Pewter. Welcome back to what is becoming a series of videos about combating the coronavirus. There are many countries now, including France, where I live, that are now closing their borders, closing down restaurants, bars, public meeting places, making everyone stay at home. Currently, since last night, if we go out without authorization, we risk having to pay a fine. Is all of this actually going to work in trying to combat the coronavirus? So I want to look at this as usual, in terms of a mathematical model and trying to predict the behavior of the virus and the evolution of the number of cases as we go along in time. So this particular video that we're looking at right now is a continuation of the one I did a few days ago. I will put a link in the window below so that you can click on it and go and look at the first video. I think you might get something out of this video if you haven't seen the first one, but certainly what we're looking at right now, the program, you will have to catch up because if you've seen the first video, you recognize the program. So we have a mathematical model with susceptibles, infectives, and people who are removed from the interaction. We have a total number N of individuals in the population, and we have certain very important parameters. Lambda is the number of contacts per unit time for a typical infective. Beta is the birth rate, delta is the death rate without disease, delta D is the death rate with disease, and rho is the recovery rate. That's the fraction of people who are infective who will actually recover per unit time. If rho is that recovery rate, we can show using mathematics that 1 over rho is the length of time in the particular category of infected people. So 1 over rho will be an important thing we'll look at later on. Remember, we had our differential equation the last time, and we showed how these particular quantities, the susceptibles, the infectives, and the removes, will progress. Note that in this particular video, we're taking daily rates, not weekly rates. So we had those daily or those weekly rates from earlier on, and now I've changed those to daily rates because I've gone to get the actual disease data from the internet for the country of France. And I want to see exactly if we can model this and how well we can actually model the evolution of the disease in France and try to predict what it is that will be coming toward us in the next few weeks. So that's the only difference, I think, between the running of the program this time and what it is that we did the last time. So let's go down here. For the data on France, we've had 23 days of data. Today is day 23, I think. And so I've put from day 1 to day 23 in here in order to try to see if I can match the observed data with the actual data that we calculate by the mathematical model that we've done. So I've taken the same function called analyze here that we had before that actually goes through and estimates the values based on the parameters that we've got. And so I run that in order to see what the model gives me. Now, I have played around with these to try to make this match as well as I can. So if we go through here and run this program, analyze, then we should get a curve of the type we saw last time. One difference here is that I've now multiplied by the population of France. I went and looked at the 1st of January of this year, 2020, and there were 67 million and a few French people in the population. And so I can use that to plot my particular curve. So let's go through here, take this and run it through R as we did before to see exactly what it is that gives. So I'm going to copy that, go down to R, and paste it into the R program. And there we have the graphs that we looked at last time. Up in the upper right-hand corner, the I is the infective fraction of the population. And in the lower right-hand corner, I multiplied that by the total population, so I get numbers of cases there. instead of fractions of the population, but the shape of the curve is actually the same. Now let's go back to the program. Here I've written down all of the numbers of cases observed in France over the last 23 days, and I'm going to get that, put it into the data sets so that we can plot those curves. So I'm going to copy that. I'm just taking those observations and copying them into R. As usual, you will get these programs and everything so that you can play with them yourself. Now what I want to do is go back to my program and plot those two functions, the observed numbers, and make one curve out of it. I'm going to make a red curve out of the observed values and a blue curve out of the theoretical values. So I'm going to go back, put that in R, plot those two functions simultaneously, and there we have the predictions are the blue curve and the observations are the red curve. So why am I doing this? I'm doing this to try to test my estimations of the parameters that I've put into the model to make sure that I have, at least for the observed data, the data we've actually seen happen in reality, how much that matches my theoretical curve. So I think that's a fairly good match. I've not proven that this is the most optimal one. If you're interested in optimizing that, we can do that maybe in another video. Going up here, I would like to look at lambda over rho. Remember that lambda is the number of contacts per infective per unit time, and rho is the recovery rate. So 1 over rho is the length of time that someone will be infected. So this number lambda over rho for a lot of mathematical models is what we call R naught or R0, which is the parameter that tells us for an epidemic model whether it will be an outbreak, whether it will be stable, or whether the disease will actually die out. And the usual theorem that we prove for the different kinds of mathematical models and also different values of rho. This lambda over rho for our model is only an approximation, but it's a good one because we have not very many deaths with respect to the entire population, and not much difference in the death rate between healthy and ill people, although it is different in our model. So this is the R naught, and if R naught is bigger than 1, it means that we're going to have an outbreak. If it's equal to 1, it's stable. If R naught is less than 1, the disease is going to die out. Here we have 3.92. Every time you run analyze, you'll get the rho value out. So if you change values of lambda or change values of rho, you'll see the new values of R0 printed out as part of the program. So with that in mind, I have some confidence now that I have pretty good parameters that I've estimated. So I'm going to go through back to the program, and now I'm going to take this program. I did several different versions of this program. This one goes from up to day 23. I want to use the same program with the same numbers. I'm going to close that down, and I'm going to look at another version of the program where now I've not changed my parameters any. I still have the same parameters because I've tested them, and I know that the first 23 days will match the observations in the country very closely. So, but now I'm going to run this instead of up to 23 days, I'm going to run it up to 300 days and see what happens within 300 days. So I'm going to go back to R again, paste that in. And there we see that we're going to have the particular characteristic curve that we saw in the first video. An SIR disease has a very sharp outbreak, goes up here to 2.0 times 10 to the 0 to the 7th, so that's 20 million cases, and then it drops back down as the number of removed increases and the disease can't really be transmitted anymore, and maintain that high level. Back to the program. I've also run this for different, and you can do this too. I'm not going to go through all of these with you in the video, but here I've said what happens if by going into confinement, we can decrease that from the value that we had originally of 0.28, if we can actually cut that in half to get 0.14. So I ran that, and I ran the plots with two graphs at the same time to see exactly what it is we got, and be able to compare the original with 0.14. So that's just cutting the number of contacts in half. That's the effect of reducing the number of contacts and the effect of making people stay at home. They don't contact as many people. So instead of the 3.92 people per infectious period, we're cutting that in half. So it would be, 1.9 or something like that. So now I've run several different values here for these programs to compare and see what that result is. And excuse me if you don't like PowerPoint, but I've done a PowerPoint presentation that I want to show you because I've able to put these results in order. So this is the graph that we've already seen that encourages me to do this, because I see that my parameters that I have for the first 23 days should actually match up with the data. And so it gives me confidence that my predictions in the future will be somewhat realistic. So now I've run this, as I said, 2 times. The first curve is the red curve is the curve where I have no confinement. It's the first curve that we looked at, and it predicts that I would have an outbreak. Notice we're here just in the first 23 days. So this is going to grow very rapidly up to almost 30 million people. That's almost half of the population. Some of you may have seen on television people saying that this could affect 30%, 40%, 50% of the population. This curve actually predicts that as well. Notice that the curve sharply drops back down as the number of removeds makes it harder and harder to support the disease in the population. Now, the blue curve takes the contact rate and says what happens if by confinement we can cut that in half. So instead of 0.28, we've cut it down in half. And notice what happens is that the blue curve is actually pushed forward in time to day 200, where here with the red curve I have the peak somewhere here around maybe day 80 or something like that. If I confine people and curtail the contact rate, that's going to make my peak come later. But notice, very, very important, instead of having almost 30 million, we have only 10 million. That's still a lot, and we try to, but we'll actually try to reduce the lambda even more if we can, in order to make that go down even more. So this is what everyone is saying when you hear them on the television talk about flattening the curve. I ran this for several different values of lambda reduction. Now, here's one just with 0.13. That's just a little bit. You'll notice that, in fact, let me go back to the last slide, this peak occurred right here around day 200, and it was at 10 million. If I go to the next slide again with 0.13, now I've pushed that back a little, as we said it always does. Pushed it back to day 220 or something like that, but I've reduced the number of cases even more. Now, you can play with this because you'll be able to download the program and run it if you know how to run things in R. I'll give you a link if you don't, so that you can try to install R yourself. It's free. But I can tell you that if you play around with this and you push this down to 0.08 or 0.09, which is just roughly a third of the number of cases, that will actually kill the blue curve. It will go away. Okay, now what happens if we push that even to 0.1, push it even further, and there you notice that we've pushed that way back even to day 400 and something, but the bump is so small that the healthcare system will be able to take care of that. Now, you might say, rightly so, that I've just run these curves as if those lambdas were the same for all time. And what we're doing right now is it looks like we're running along with lambda equals 0.28, and we're going to change that if we put people, make them stay at home and don't contact people. We reduce that. What happens? Where are we on this red curve already? And where is it going? Where are we going to go if we suddenly change lambda? Well, I ran that as well, and taking the one model up to day 23 with the original lambda, and then proceeding from day 23 on using the new lambda. And by doing that, here I have, this is the result if I switch from no confinement up to day 23 and then confinement after day 23 to day 200. Notice that the peak is actually pushed back to about 150 or 160 or something, and it's down to 10 million cases. So our conclusion is confinement does work. It will decrease significantly the number of cases that you actually have, so you will decrease the number of deaths, you'll decrease the burden on hospitals. If you push this down low enough, in fact, you'll kill the disease out. So please go into voluntary confinement if you haven't already, and we'll all get through this together. Thank you very much, and I hope to see you in another video.